So is everybody just seeing the one screen now? Is that?
Yes.
Yes.
I guess we should probably get started, Rick. It's 8:02.
Okay.
I think we've got about 12 participants. We'll probably pick up a few more as we go.
Okay. So when Bob contacted us to initiate a conference here between us all, he gave us a list of about 427 topics to cover. And from that list, I exaggerate, I picked out several things I thought would be important to at least start with. And maybe if this is found beneficial, we can schedule another one and reform some additional topics. There's still quite a bit of material to cover tonight, this morning. And if you have some questions or if I'm going too fast with something and you feel it's important and you can't wait, go ahead and interrupt and we'll deal with it. But I would, if possible, like to try to run through this, and then we can have questions at the end for anybody that wants to review it further or go through that. So with that, we'll get started. So I want to welcome everyone to the first ever Matrix Panasonic Sanmina Material Seminar. And of course, on behalf of Matrix and Panasonic, we're very pleased and thankful, excited for the opportunity to present today. So the outline that we're going to cover, if I can go to the next slide, there we go, is pretty extensive. We'll go through some of the materials that are offered and that are available today. We'll go through some of the specifics about those products, and we'll go into some details about copper foil, talk about spread glass, and then talk about some new things that are on the horizon as it relates to materials in the Panasonic offering. So as most of you know, the product line that is available through Panasonic is quite extensive. Not all of the items, of course, were in North America that we talk about and deal with. And I'm going to use can you see my cursor as a pointer?
Yes.
Hopefully you do. So there's a whole plethora of products that are available to go through different markets and different applications, and each of those markets have a specific need that is more important than others. And we're going to talk about the Megtron series, which has to do with low loss, high speed materials, and at the 5 o'clock thing about Philios and some of the thinner materials and the flex type materials, and we'll focus on those markets. So these are other areas we just kind of bring up as the product offering, but we're going to get more specific with that as we move to the actual materials update portion. So as we look at just the general mapping of materials by loss and by thermal robustness, the lower left-hand corner is the FR4 type world, and as we characterize that to the right, it's more for the electrical performance. So as you go to the right on the chart, you get higher performance, lower loss materials. As you go up on the chart, oops, I'm going the wrong way, sorry. As you go up on the chart, you get the thermal performance, so reliability and performance, the higher on the chart. So the upper right-hand corner would be the high-performance products, and the materials that we'll be talking about today. Hello? There we go. Talk about today are MEG4S. We're going to talk a little bit about introducing G for those that haven't. At the end, we'll talk MEG6, halogen-free, but the other new material here, the high-performance one, is 7N. So these are the 4 materials that we'll talk about on the rigid side, and then we're going to spend some time talking about LCP as well. So as we get started with that, the 4S. 4S is an improved version of MEG 4. It's got higher heat resistance and thermal robustness. Basically, there were some issues that would come up from time to time, and we call those special PCB constructions. And you may have be aware of some of those. But essentially, it's the same resin system, MEG 4. MEG 4S is from MEG 4. It's the same UL. And if you think about it, the same components are used, and that's why it is the same UL. But those components are pre-reacted in a way that makes it more thermally robust with it. So it's the same components, but we get higher performance. So these are some of the special PCB constructions you may have been aware of before or may have heard about. If you haven't, we're introducing them here. Of course, the hybrid construction where you've got MEG 4 on the outsides and you've got another bond ply in the middle to try to bond those subs together would be one. On the outside layer, HDI buildup technology. You might be familiar with seeing some eyebrow cracks from time to time. And then, of course, the two sequential laminations where you've got a bond between two subs. So all of these were extenuating circumstances where MEG 4, really you had to have an optimized process to be able to make this kind of stuff work more successfully with that. So 4S addresses that, and it does that by improving, like we said, the thermals of that. So as a result of the pre-reacting the components, we get a higher TG. It's a 200 TG. This Z-axis CTE is improved, lowered. We have actual peel strength is improved. The inner laminar bond is improved, which is a key to that. We get a T288, that's a higher number. And the electrical properties are the same because it is the same product. So with all of these combined improvements with that, we get improved thermal and adhesive properties that allow it to handle the special, sequential lams, the HDI buildups, and those types of designs now. With the change to the 4S though, there is a little bit of a shift on the prepreg rheology. If we look at the standard at MEG 4 is like the purple, light purple there, and there's a slight shift with the MEG 4S as far as the viscosity goes, a little bit lower with that, a little bit, so we're concerned a little bit with the storage time with that. If we look at resin flow to the right of that on the chart, a little bit of the shift where the blue is the MEG 4S, so it's a little bit lower on the resin flow. So we're concerned if we're going to store this an extended time, we want to make sure we're storing it properly and extending the shelf life. We store all of our prepregs at matrix at condition 1, the low storage, so that shouldn't be a problem with that. But just to bring that up as just something to be aware of with MEG 4S. So overall, very stable, a very reliable product, a great improvement for that, and has done very well. And we'll move on to MEG 6. I don't have a lot of slides for MEG 6, but I did want to just kind of review. There is 6N available, which is the low decay glass option with that. And the original MEG 6, as many of you know, is 6K and designated as 6K. And we also have 6G now, and that's picking up a lot of momentum with it. All three of these are the exact same resin, so it's all MEG 6. It's all made the exact same way with that. The difference is the MEG 6N is E-glass, but it's low decay E-glass. The MEG 6K and the MEG 6G are both E-glass, but they're made from different suppliers. So the cost of G is more economical with that. You can see the properties are exactly the same down the line between the two products. And of course, the UL between all three are the same because it is the same resin, and that's all UL cares about. And so those are all, the K and the G are equivalent in performance and property, and you'll see the only difference here basically there's a change in the decay because of the low decay glass. You get a bump in the decay and a little bit of bump with the DF as well, but the primary purpose of the low decay glass is faster signal performance with the lower decay. MEG 7, that's the next generation. We're talking about high performance. When it was conceived, the idea was for MEG 7 to be half the loss of MEG 6, be higher performance with that. So you can see the target here, 2.002 at 12 gig for the loss factor with that. So it's approaching PTFE, but much better than MEG 6. There's also a low decay glass option with that, 7N, and that seems to be where a lot of the activity is when we're going from higher performance from MEG 6, is going from MEG 6 to 6N, and we'll talk a little bit about that in some of the charts here. But basically, the MEG 7 is a high TG material, a high TD material at 400. It's got very stable X and Y CTE, low Z-axis expansion. We've got a T288, of course, it performs very well. So very reliably performing at thermally, and then also throwing in the electrical properties as well that do very well with it. So overall, we've seen very good results with MEG 7N. The 7 is still the high TG material, again, same properties, but without the low decay glass. And then also put down the MEG 6 just for a comparison with that. If we look at the loss factor as it compares, you can see that the MEG 7N, as far as we're looking at dB loss per, in this case, per meter, there's less loss. The higher on this chart it is, less loss across frequency with MEG 7N. The next on it would be MEG 7. Of course, the MEG 6 is here with that. So we get good transmission signal performance with MEG 7N. So if we're looking at going from a MEG 6 to a MEG 7, just kind of in general, 10% improvement on the transmission loss. If we go from an E-glass to a low decay glass, you get a bump in performance also. And then using HVLP for all of these, if you go from HVLP, now we have available HVLP2 on MEG 7N to give us overall kind of a 30% just general number of improvement. Of course, there are other things like oxide and some things that will play into that, but just give you the general number, going from a MEG 6 with HVLP to a MEG 7N with HVLP2, you get better performance with that. A little bit about HVLP2. So you might think that, well, now we have even a smoother copper that we have to deal with. That's not really the case. So the RZ values are very comparable between a conventional HVLP and the HVLP2. But the difference is the structure. If we zoom in here, you can see the structure on the standard conventional HVLP is very needle-like, and we'll call that rough, for lack of a better term with that. And here it's a little bit smoother. So the depth of it with the RZ is similar, but it's kind of smoothed out. And so with the ultra-low roughness on them, there's more of a shape. It's kind of a rolling hill as opposed to a speed bump kind of thing. And then also included in the HVLP2, they modified the siling so that way the treatment on there, it promotes adhesion. So we're not losing with the peel strength with that. So it's a little bit shift in the technology to help with the performance. Moving on to the LCP. So the Panasonic product offering is the RF705S. That's the designation for LCP. And I pulled this slide in. It's from our Philios presentation as an introduction to the Flex product. Panasonic offers a Philios RF775, which is a polyimide adhesiveless flex material that's been performing very well, gaining market share. It's not a topic for today, but I just bring it up to show that we do offer that. And also the Matrix Plus line of cover-lay, bond plies, and adhesives are available as well that complement the Panasonic Philios products. We also have in Santa Clara Flex Center of Excellence Conversion Center that's available to cut from rolls to supply whatever panel sizes are needed, and we have excellent service and support to help with the product line as well. Bob Berg is our product manager for this line and heads up that operation with it. But today we're going to talk about the new Flex product technology and what that has to do with covering all these markets that we're trying to do with the Philios. It's a really busy slide, but the Philios product with the polyimide is the top line. We're really going to talk about what's in this space right now with the antenna modules, high-speed cables, optical transceivers, milliwave radar, those type of applications where LCP can fill a need and be a solution for that type of a market. As we go on to just talk specifically about the Philios, the applications, antenna, high-speed data, and actually 2012 won an award at the JPCA for a new product introduction with that. So it's been one of these products that's actually the market's just exploding. It's driven by the high signal integrity benefits, and we'll talk a little bit about that, the low moisture absorption, chemical resistance, make it all a very good solution. So what is LCP? If you go on the internet and ask what LCP is, I came up with 76 different acronyms for LCP. It was interesting. I thought it would just be so common that it would come up with circuit board material that has electricals and chemically resistant, but there were things out there like we're describing guns. There's a Ruger that is actually a light, compact, powerful gun. That's LCP. There's a long chain polysaturated fatty acid. That's not what we're talking about. And there was even one that was internet related. It's a link control protocol. All of you guys that are out there on the internet, you probably are familiar with that LCP. And no, we're not talking about the League of Canadian Poets. What we're talking about is it's a liquid crystal polymer. And these are for all of you guys that are chemists out there. You can look at this. And all of you that want to go back to your high school chemistry days and figure out all the strands, how it put together. But really, I'm not a chemical nerd, but one of the things that is, it's a highly ordered structure is what I get out of this part of it. And in both in the melt and the solid state for that, and it's a long chain. So as a result, it has these characteristics that we're talking about being thermally resistant and having good electrical properties. But I just thought I would throw that in case that means something to you. You want to know what it was, but we're done with that one. For the benefits of where it's actually got a market for it is in this chart here, as you'll see on the left-hand side, we're talking about transmission loss. And from the top, it's a lower transmission loss to the bottom, where it's a little bit larger transition loss. So a standard polyimide flexible product is a little bit lossier than the liquid crystal polymer, the LCP, but you can see it's approaching the coaxial cable. So the coaxial cable is kind of where we're headed as far as the performance that we're looking for and trying to duplicate or to use. So to show it a different way with that, since to get the same performance with that, one way to do that is on a shorter line. So this one's showing the Philios product here is got a 1 loss dB at 5 centimeters, and the coaxial cable is a little bit better than that, can actually get to that in 10 centimeters. So if you're looking for a certain loss, all we have to do is minimize the length of the circuit for the Philios to get the same performance as the coaxial cable. And where that comes into play is a couple different ways with that. One is shortening up the actual line would be one way if it's a smaller appliance with that. But if you look at the top here, we look at the dimensions of the coaxial cable itself, 0.8 millimeter And so the actual space savings is another way that this product can be superior with that. If we can come up with a double-sided product that's LCP, you can see that it's 0.2 millimeter in height with that. So we get a 75% thickness reduction going to an LCP. And then combine that with a shorter line length with it, then we can approach signal loss that's comparable to an actual coaxial cable with that. So that's kind of where we're headed with something like that, is to find those applications or people that are looking at replacing a coaxial cable with a high-speed, thinner material with it. Some of the actual properties that make that possible, of course, the low DK, the low DF, make it excellent for high-frequency properties. We've got the water absorption, so it's ultra-low moisture absorption when compared to other materials in that same space. The peel strength is excellent. We get good bond. It is a 94V0, flame resistant. It's very dimensionally stable, excellent dimensional stability with it. And to show that, so here's the decay across temperature. And if you look at the yellow line, so that's more of a polyimide type product with it, it falls off after the certain temperature. And you can see that the PTFE is very stable across temperature. So that gives it an advantage in different operating conditions with it. Similarly with the DF, so the loss factor with that, it is very stable across. It does change a little bit as it goes out, but the same thing for ceramic. But you can see the polyimide that might be used today with that just can't handle the higher temperatures with that. So we get good performance with the LCP, and you can see actually the low dissipation factor as well on the chart. So it's got excellent loss properties, approaching the PTFE there at the bottom. So if we look at that compared, this is the 775 is the polyimide flex material, the Philios. And the two things about it. So on the left-hand chart, we've got the decay, which is the dielectric constant. There is a shift between the polyimide at elevated temperature humidity as opposed to the as-is condition with that. But you see there's very little change in the LCP between the two different conditions, the as-is and then the elevated temperature humidity cycling with that, very little change. And similar with that on the loss side of that. So the dissipation factor, there's a shift from the as-is to the conditions and a very tight condition between the as-is performance to the conditioned performance. Another way to look at that too is against moisture. So the moisture absorption, we see the LCP, the two conditions as is, and after moisture absorption, they almost line up right on top of each other for LCP. And you can see between the polyimide, the as is versus the moisture absorption, there's a degradation in the loss factor with that. So there's more loss. So the LCP is very stable across temperature and across moisture. And then processing-wise, it gives some real advantages as well. The RF705 material is very stable, and this is one of the charts that's been used before to characterize that. You can see a very uniform movement after etching and then after a thermal, after a 150 degrees C for 30 minutes. So this would show any of the stresses that may be inherent in the materials that may contribute to dimensional stability or instability as it would be. And so with that, you get more consistent processing. So to go with the LCP, there is a bond ply available. It is the RBM17 bond ply, and it has some very, very good properties that go with that, so allow it to bond the LCP together. And we can look at, of course, the dielectric constant's got to be low, otherwise it takes away from the performance of the LCP. We're also looking at the dissipation factor. If we're looking at the LCP, so it actually exceeds that 0.001 as is, 0.0014 dissipation factor. And the other part has to do with the lamination. So this is a typical, I guess, you might say current lamination for LCP. It's quite complicated if you're familiar with a press cycle. We're showing pressure, multiple pressures at multiple times, and we're showing multiple heat rises, the stepping up of temperatures, and then also the very high temperature, 305 degrees C, to be able to laminate it is very challenging. So with the RBM 17, this is more of a conventional type cycle that would be used on other type products where we've got one constant pressure and we've got heat ramp that goes up to 150 C and then on up to the cure temperature of 180 C, which is not anywhere near the 305. And it's very close to what is being used today for many products conventionally being laminated. So the RBM 17 is a good option in that case. So more conventional lamination cycle. So something else to introduce, I was torn between putting this at the end under the new technology, but I think it fits more because it is part of the LCP specifically, and that has to do with EC copper. It's electrically deposited copper, but it takes on a little bit different form. So if you look at the structures, we're going to talk a little bit more about copper foil later, but basically the EC copper is electrically deposited, which would be the same as standard electrically deposited, at least from the start with that. But after it goes through the lamination process, the structure changes. So that structure changes to what looks more like a rolled anneal type structure would be. But what it does, though, is it gives actual improved flexibility and crack resistance. So it goes through this recrystallization process through the proprietary lamination cycle that Panasonic uses with that. And then you can see in the SEM photos of the cross-section how those structures are actually changed. So this gives it a very good product that can be used, high reliability, especially with that, and crack resistant. Some of the properties about that, you can see that it has a low RZ value. We'll talk a little bit more about that compared to the standard electrodeposited foils. The insertion loss is lower. Peel strength is still comparable with that, very good. It's comparable especially compared to the RAs, which are difficult with that. Heat resistance is improved, and then the test cycles are the same as the RA. So we get good performance and good crack resistance with the EC foil with it. So the recommendation really would be if we're using the LCP product, to use the improved EC foil for improved bending, flexibility with that. Use the LCP, of course, for the high-speed, high-frequency applications, and then the bond sheet, the RBM17, of course, would be to pull it all together with that. So currently the product that we have... Yep.
Can I ask a question? Does that EC foil only recrystallize at the high temperatures of the LCP process, or would it work at lower temperatures as well?
So that part is we talked about is a Panasonic proprietary lamp. So I don't know what they do in that process when they're making these the core. So I don't have that information.
Okay, that's fine.
So currently what's available for the product line is we're talking about 1, 2, and 4 mil LCP with with a 1/3 ounce and 1/2 ounce that are currently available. And then we're looking at adding the 1/4 ounce coppers and a 3 mil product here shortly. So hopefully those will be available soon and we can have the full product line. But currently it's 1, 2, and 4 mil dielectric and 12 mic and 18 micron coppers. And that's the LCP part. So now we'll transition from the products and kind of talk a little bit about copper roughness and how that impacts the signal. And I thought as we do that, we probably should talk a little bit about understanding of copper foil, for those, I guess, that may not have that information with it, we can just review it. It's a slide that's been around a while. Basically, the ED copper foil is electrically deposited onto a drum, and it gets plated. And as it gets plated on this drum, it gets pulled off and rolled up onto, I think I went through another slide here. I thought I had another one there. Anyway, it gets rolled up onto the drum, and you can see on the top part, the drum side is very smooth because that drum is a titanium drum, and it's pristine condition with that, produces a very, very smooth foil. A mirror image of the drum is onto that smooth side, the shiny side, we call it the drum side. The opposite side, the matte side, where the chemicals are, that actually was where the dendrite growth is. And you can see the topography on the matte side. Once that's created, there still is several processes that it goes through, and that's a treating process that the copper manufacturers run them through, typically to grow some nodules to help improve bonding, encapsulate the alloy, make a barrier layer for they have some thermal resistance, some undermining resistance, and then at the end of that, an oxidation treatment with that so it doesn't oxidize, a chromate silane finish that goes on there to prevent it from corroding. So those are all steps that go into making copper foil, and as we know it, the shiny copper foil. And those actually are pulled off into into rolls. And then if we're looking at them blown up with that, and we have some more slides that talk about that, but understanding that part, these are some typical SEMs of the surface. Again, the drum is actually a very large drum, and I was trying to figure out the other day that what the guy is standing there, but I think that is just to give you an idea on how big those drums are. They can be quite large compared to a guy standing there with it. But again, the drum side is a very smooth side. We call it the shiny side. The opposite side of that is the matte side. And that's where all the dendrite growth is and the topography of it. And you can see the faster, the thinner the copper, the faster this drum can go, and the slower, actually the thicker the copper, if we're going to 1 ounce, 2 ounce, then the drum has to slow down quite a bit to be able to allow the time to plate onto that. And the copper manufacturers control that. They control the baths with it, and all the tensile strength, the elongation, the roughness, that's all being done in that manufacturing process. So there are different topographies. Years ago we were looking for bond strength, so we wanted more topography, more like the conventional electrically deposited foils with that. But now we're looking at improved signal performance, so we're looking at lower profiles, which would be a VLP or a HVLP, and this is showing even a flatter foil with that, almost no profile with it. But the key to it, though, is also the other option is available is RTF. So this gives you an idea between the shiny and the RTF. On the left-hand side is the shiny foil, and if we're looking at the shiny side, it's called the drum side or shiny side, there's almost no topography at all. And the top left-hand corner that I'm pointing at here is the treated matte side, and you can see that that has some additional topography that we talked about during that treating process once it was done. On the right-hand side is an untreated matte foil. You can see that just has the basic dendrites that were produced during the plating process. And then below that is the treated drum side. So this has got additional topography that's plated onto what used to be the shiny side of that. The importance of that, too, is there's two things with it. One, this gives the treatment enough to enhance the peel strength, so the laminators can use this, what used to be the shiny side, what still is the drum side, but now it's treated. They can laminate that down against the laminate and have that be part of the core material. And that allows the opposite side, which is the matte side with all the topography, to be up and be able to have additional topography during the multi-layer lamination process. So as you building a board, circuit board shop, Sanmina can take advantage of that treated side, actually with the matte side that has the topography already there. The other benefit, and I don't go into that here, it may be a good topic for another one, is actually the dendrite structure is a little different. By flipping it over, the structure the grains are smaller on the drum side, and that gives a better etching characteristics because of that. And that's the other benefit of having the reverse treat. So there's a couple reasons for that. But the key, what we're talking about, is really understanding what the effects are of these treatments on the signal performance with that. So the application would be is we want to make sure we've got low profile copper to be able to have better signal speeds, a better signal performance, less loss. But part of the challenge these days, because we have different copper roughness values that are available now, how to measure those low profiles has become a little bit of a challenge. Some people are wanting different values. RA is something you might hear, RZ. Now we're talking about RMS. They're all measuring things, but they maybe have a little bit different values with that because of the way it's measured and because of the way it's calculated. The RZ value is the one that's most common. That's what's used most with that, but the challenge with that is this actually measuring that part of it. The RMS is being asked for now, but it's not something that's real commonly available and requires special equipment. Part of the challenge to get the special equipment is if we're looking at the tooth structure that's very small, you have to have a very small stylus to be able to get in between there and be able to actually measure the peaks and valleys of that. So even at an exploded view here on a VLP copper, you can see the challenge of a 5-micron stylus just can't do it. So other methods are being developed, other methods are being explored and trying to come up with a way to do that. And maybe we'll see something here in the future, near future, that will be able to characterize these a little bit further with that. Maybe IPC will help out with that, coming up with that. But you can see here how it's a very small structure, but you can see RA value versus RMS value versus RZ values are very different, looking at the same, measuring the same area with that to come up with a different value. But today what we have really to go by with it is the RZ. That's what the IPC 4562 talks about RZ and has been accepted with that. The only issue really with that, not really an issue, is there needs to be another designation here. We've got down to V, which is very low profile, and that's 5 micron or less with it. And we have coppers that are less than that for sure. And so this is what we have to work with for today. But to apply that to the Panasonic product line is if we're looking at Meg 6, we're looking at Meg 7, we're talking about HVLP, which is low profile. We're talking about reverse treat. But you can see here the standard foils, they're above that 5 minimum for the VLP category. They're a little bit rougher with that, depending on which copper weight we're looking at. But really the one we want to focus on, though, has to do with the reverse treat. We talked a little bit about reverse treat and how they manufacture it and how they treat it. And that's why the treatments of the drum side has additional topography compared to others, because it's not shiny. There is a treatment there. But the key for the reverse treat that Panasonic chooses is that it is less than 5, which is lower than the VLP category, or it fits into the VLP category. So while it's reverse treat, that doesn't mean it's rough. And so that's how we're able to get good signal integrity using reverse treat. Not all applications have to have the high performance HVLP, which of course is the best available now with less than 2 typically with that. So either one, the reverse treat on Meg 6 or the HVLP and the HVLP2 give all good electrical performance with that. And to show that, we could look at the dB loss graph again, and basically the upper side of this is the HVLP with black oxide, gives it the lowest loss, so the least amount of loss across here. And you can see the category here is the number minus 14, minus 16, minus 18. Those are all more higher loss values with it. So if we're looking at the HVLP, it's the least loss, and then the next one happens to be the VLP, which is the next category with that, whether it's got black oxide or different oxide treatments. Well, the VLP has better performance than the standard, of course, and these are the standard with the roughest foils and the roughest oxide treatments as well. So there's more loss, of course, with those. If we look at just a comparison between standard foils and VLP, you get the point here again. The VLP performs better than the standard, and if you look at the cross section, of course, it's much rougher for the standard foils. Traditionally looking for better bonds with that, but now we need not only to have the bonds, but we have to have the smoother copper for the better electrical performance. Same thing with the oxides. So over the years, the oxides have the primary purposes for bond, but now not only does it need to have a better bond, it also has to be able to minimize the loss, because all the good things we're doing, the extra money that we're spending on the high-performance foils can be lost with having an oxide that doesn't perform. Here we've got two different oxides, so we're showing the high profile is the one that has the most loss. This one is actually flipped upside down now, the chart is, but the higher loss values are on the top side of the screen, and the lower loss values here with the lower etch or the optimized oxide. So there's a whole way to go through and measure all this. This was just outlined. If anybody interested in that, I'm not going to take the time to break that down, but there is a whole test method procedure for measuring that. It's the S21 transmission loss is what we're really they're pulling off of the network analyzer. So we can talk about that if anybody has any other questions with it. Again, this is just another breakdown comparing different oxides. And the point being here that the none value, there's no oxide, actually has least amount of loss compared to anything that roughens it up and it gets the highest. If you have a very aggressive oxide, then you get more loss because of that. There are a lot more oxides in the market, and just the point would be is that oxide matters and need to categorize that. And it kind of fits that these, the rougher, more aggressive, you can see the topographies on them, are the ones that actually have the highest loss with it. So that's kind of the impact of the copper roughness, and then also the oxides on signal performance with it. So we move into the glass. So over the years, we've been talking about spread glass, and I think spread glass was really developed for the laser microvias initially with that, trying to make it more ablatable. Then the electronic designers got a hold of it, and it actually provides a little bit better solution for that. So all the fabric that's used for Meg 6 and Meg 7 are spread glass. They're spread weave. And there are some that are actually high spread or ultra spread that are used with it. And that applies both with the E glass, with the Meg 6G, the K, and the 7, and also with the low decay glass, Meg 6N, Meg 7N. So if we just compare, these may be review, but the standard glass that is not spread is the filaments are kind of grouped together in a bundle, and it forms kind of a circular pattern with that, and it shows the gaps here as a window. So there's a gap between the bundles. The spread glass kind of spreads out those filaments and makes closes in the window, where it makes that less visible with that. And it looks here from the top view of that, these windows on the original would be filled with resin, whereas the high spread glasses, there's no windows with that, there's no gaps. And so that ends up having a more uniform effect with that. And if we've seen these graphs before where in the red line with the line condition A would be over the top of glass, and line condition B would be where there's gaps, where there's resin, glass, and what that does is that changes the signal attenuation then and the timing of that, because again the decay, which determines the speed of the signal with that, gets lower when you go over pure resin and gets higher when you're going over pure glass. So it's just the ratio of that. And so that affects the signal and makes it inconsistent. So by spreading the glass then, both the condition A and B, and compared to condition C, it's all made pretty much uniform with that. So the wave pattern and the timing of the signal becomes more consistent of that, no matter what. And so this allows for where in the past where you have to rotate maybe a board or something on a panel to try to get away from being over all glass and being over all resin, it still didn't get rid of the gap. So there still could be, it's a better option with that than just running over the standard glass with the gaps, but this is the better option than now, at least to make it more consistent and predictable with that. So if we're looking at a slide here that the spread glass actually is a solution for, signal performance with it as far as consistency with it. But one of the things I don't think it gets talked about enough, and it may be just a fact of some of the resin systems that we're using that are lower flowing. So the flat glass is a solution for uniform signal performance, but I would say the flat glass also can be a problem. Actually, it shouldn't be a problem. But really, it's more of a challenge for filling heavy copper. And from the tech service side of things, that's something that has been one of the issues that needs to be, educated with that for especially for new users with it, and to try to quantify some of that too. The lower flowing resin systems present one of the challenges with that, but there's a lot of factors that influence the flow and the fill. And of course, the rheology is a part of it, the process, the lamination cycle. The board design itself has a lot to do with it, number of layers, the copper weight, of course, how thick are those copper layers, and the copper distribution. And then many designers, they want to have a very thin dielectric space, and of course that then starts getting into the prepreg. So that's really, I'm not talking about all these other factors. That could be topics for another discussion. We'll focus in on the impact and what we can do with the prepreg itself and how that would influence that. So if we just look at all the spread glass, we're seeing the 106 in the old days that were used as the thin glass. It has a lot of gaps. The 1080 in this case is spread, but it's not spread enough because of the limitation on the counts in the X and the Y direction. There's just not enough to spread it out to make it a high spread material. The 3313s and 2116s are very heavy glasses, and they just can't be spread anymore. They run out of real estate with it. So really the high spread, the ultra spread glasses here, the 1027, 1035, 1067, 1078, these are all the glasses that are what were considered the ultra spread or high spread glass, and they're really optimized for that because of the number of yarns. They're balanced in X and Y. 1035 has got a balanced weave with 66 to 68, and 1078, 54 in each direction. But the reason why they're in these columns because a 1078 is very comparable to a 1080, and we'll just look at the thickness of it and the weight are very comparable. The same thing for a 106 and a 1035. The 1035 replaces the 106 in both Meg 6 and Meg 7, and that's because of the thickness of them and also here the weight. So that way it can be very comparable in the stack up with that. And the weight is very important. We'll talk a little bit more about that as we get into that. So just these are some details. I know it's regarding the glass, and but I think it's an important part of the equation as we move forward in filling heavy coppers with it. But what also we have to understand is the resin content. So typically if you're looking at a lineup and you're looking at a stack up, we want a certain thickness, and so we're able to go down the line. So we have a 1035, and then we have a resin content that's associated with that, and then a typical thickness. And this is just thickness between copper planes. And between Meg 6 E-glass, Meg 7 E-glass, it's basically the same. So if we have a 75% 1035, that gives us 74 microns of thickness, and the same thing for the Meg 7. We've got 74 microns of thickness, almost 3 mils. And if we're looking at the end glass, I want to bring this up too, in case you're used to seeing a high resin content. If we're looking at the 74 as the thickness we're looking for, almost 3 mils, there is that available on Meg 6 and Meg 7, but if you'll notice though that the resin content is bumped. All the low decay glass resin contents are bumped by 2%, and that's to keep the exact typical thickness in line with each of the glass styles. So if you're used to seeing on a regular Meg 6 a high resin content of 75%, there is 75% available on the low decay glass options, but just keep in mind that that doesn't give you the 74, almost the 3 mil. You have to go to the 77%. So I'm always pushing for more resin, and I don't want to ever have anybody ever a mistake of going to a lower resin content when you're really looking for a higher resin content. So I point that out. The other thing to understand is the resin content percentages for prepregs are relative to the glass fabric that we're talking about. So we're looking at a ratio between glass and resin. So a 75% 1035, it's 75% of what makes up a 1035 prepreg is resin. And the same for 75% of what makes up a 1078 is the resin. The same thing for the 2116. And the higher resin contents, of course, should be related to more resin available, but that's only if you're talking about for within each specific glass fabric. And to illustrate what I'm talking about, to understand that more, we got a percent of resin content versus the resin that's available there. If we have 2 half gallons of milk or 1 liter, however you want to look at that, of milk, and you've got 70% in one and you've got 75% in another, we know that the 75% has got more milk in it or more liquid in that part or more resin if we're talking prepreg 1035 with that. But the reason why it's so important to know the weight and thickness of the glass is because it's a different container size. So if we happen to have a 2116, maybe it's 56%, and we compare that to a 75% 1035, which one has more resin? Which one has more in the container? Well, we know the container size, so we know for sure that the gallon product that has more than half, it definitely has more than the half a gallon less than full. So if we were to relate that to, what does that really mean? If we take the 75% of a half gallon, it really equates to 37% if we're looking at the same container. So it's important to know what the container size is or what your glass weight is, your glass thickness, to be able to help predict what you need for fill or what the best option would be for thickness and fill. So again, this is another way to look at that same chart we were at with the glass fabrics and with the thickness values that are for each of the glass fabrics. And here's the weight, the relative weight for each of them, both in grams per meter squared and ounces per yard square. And you can see that the 1027 is a very lightweight glass, and 0.56 ounces per yard square compared to, it's almost 3 times less than a 1078. So it's an important factor because when we start talking percentages, those become very significant with it. So if we look at the actual resin contents and the thicknesses that we were talking about, so for each of these, I picked each of them have 75% resin content, 1027, 1035, 1078. And each of them have a predicted thickness that would be between solid copper. And so those typically are what used when doing the stack-ups. I'm looking at what dielectric thickness I need, and so I go to my table that tells me how much I've got there and compare that to what my design says, and okay, I'll pick a 75%, whatever it is, 1035, and off we go. But we have this prepreg thickness, so we know this dimension from top to bottom as a theoretical thickness on average with that between 2 solid copper planes. And if we know what the glass thickness is with that part, and then that will help us, I kind of came up with a way to kind of quantify what would be a theoretical amount of resin that would be on either side of the glass for each of these. And it makes for a very interesting table here. So I'm calling this a theoretical butter coat or surface resin would be maybe a more technical term with it, that if we're looking at a 1027, we've got 6/10. If we take the overall thickness of the prepreg, subtract out the glass, divide the remainder by 2, this is where I'm coming up with the butter coat with that. And you can see the relative differences. Even though these are all 75%, they're very different for how much resin is actually on the surface based on our little calculation here with that. And I'm not, so that's one factor to consider when you're looking at what's available to fill. I always default to a 10, 78, 75% whenever I can, just because of this fact that it's got the most resin on the surface. In the column next to that is what I'm just kind of, it's a reference value more than anything else. I'm not considering the density of the resins. I'm just doing a percentage of it. If I know the glass weight and I know the percentage of the resin to the glass, I've come up with this little factor here that I use, and you can see that not only does the 1078, 75% have the most resin on the surface, by volume, if we look at it that way as a factor, it's got the most by volume with it. And you can see the 1027 has got the least amount. So that would be one that I would caution I would use this as a specialty glass. It's got its purpose. It works very well in its application with that, but I wouldn't promote it as one to fill heavy coppers with that part. So, and it's definitely 75%, but it's 75% of almost nothing means it has almost nothing for resin. So that's kind of the way I term it with that. So I'm looking to use the 1078 wherever possible. Now with the heavier glass.
Hey, Rick.
Go ahead. Yep.
Yeah, Bob Jaff here. Hey, you can put in at least almost 2.5 times as many plies of the thinner material. So even though it doesn't have as much butter coat, you end up with more resin, more fill resin per mil of total thickness with a lighter cloth.
Yes, we'll get to that. I've got some slides on that too.
All right. Yep.
So if we look at the very thin in this calculation, the very thin 3313 surface resin, 3/10, and relatively speaking for the 2116, that would be a little bit of a concern for filling some of the copper features. But if we go to the right and we look at the resin weight that's available, these are some of the higher resin weights because the glass is so thick and so heavy, relatively speaking. These 50% of something that's very heavy gives amount of resin that's available to fill and to help to fill with that. So I kind of combine looking at the resin weight, if you will, resin weight factor. Maybe I should just get rid of the ounces per yard square and use this as a number or a factor of that. Might be a better way to do it for the way I've calculated it. But anyway, I use it as a reference only. That's why I say it's theoretical. But it's something that at least we should talk about with that when you're trying to discuss optimizing thickness versus the amount to fill. So what Bob was talking about then too is if you're putting multiple plies together, you actually if we're saying we've got 75%, let's say for theoretical purposes here, we've got about 1.5 mil on the surface of each of these plies, which means we have 1.5 mil on the inside where these two plies are together, which actually doubles the amount of resin in between the two plies. So that's all good because we have additional resin that we have available there. But the concern is, and the kind of the unintentional consequence of the spread glass is it doesn't really allow for the transfer of the resin as it does. So at 1080 and more open weave, we get more of the transfer of the glass to go through it, where we don't see that as much on the spread glass. It acts as kind of a filter there that holds it together. And you can see here my little diagram between these two on the 1080 side, you get more of a squeeze together, so the resin that's in between gets pushed into fill the heavy copper areas, where you don't get as much of that with the spread glass. It tends to hold the resin in between the plies. So that's why I think it's important to really consider the surface resin as the amount that you have available to fill. So there's two things with that. So one is possibly having glass stop because of the heavy copper feature, depending on what it is and how much you're trying to fill. Because this glass is getting pushed to those copper features, you may end up with a situation where there's not much resin between the actual glass and the copper feature because of the low pressure area, both top and the bottom with that, where you get a little bit more space because of the open weave with it. Sorry. And then the other part of it has to do with there could be voids in the side where the spread glass, because we're not able to take advantage as much of the resin. In the old days, it was more plies of 106, more plies of 1080, because those weaves are so open with that. And like Bob was saying, there's a lot of resin available by multiple plies, but that's really predicated on the fact that it could actually get through those gaps and get into the areas that are high pressure. So it's not necessarily the case with the spread glass, so you have to keep that in mind with it. So my part is, why is the spread weave a challenge? Well, because the spread glass impedes that resin flow from one side to the other. That's really the main purpose of that. And I don't see as much of a benefit by adding more plies because of the spread glass. It doesn't necessarily add more resin where we really need it to be in the fill area with that between those copper features. So the surface resin and the resin that's available for filling the volume there are really the key with these lower flowing resin systems with spread glass to filling that heavy copper. All right, we'll keep moving on here. We're at home stretch. Got a few more slides here, and these just have to do with introducing some of the new products. So the R5375, the much awaited, highly anticipated halogen-free Megtron 6 is being it's available in a test case right now, so limited quantity with that, limited testing that we have going on, but we've seen some very encouraging properties with the Meg 6 with it. So in particular, of course, it's got a high TG, which makes it more robust with that. It's got a very, very high TD, so we're encouraged with that, so very stable in the thermal performance with it. And then the one I wanted to point out too is that I'm used to seeing Meg 6 and Meg 7 with high T288s, but here on this particular chart we've introduced the T320, so even a higher stringent test with that, and it performs very well. So those are very good properties. So a low Z-axis expansion, a high thermal conductivity for those higher than Meg 6, for those that are interested in that, could be a benefit as well. Very similar DKDF values with it that we're used to seeing with Meg 6, so that fits into that same category. And then, of course, being halogen-free is the bonus with that part. So the Meg 6 thermal and electrical performance that we're used to, but with a V0 flammability rating with halogen-free. So we're looking forward to seeing that as it becomes more available. This was one that was on Bob's list of topics that we happen to have, and we can introduce that. The R5775W, which is a tighter thickness tolerance Megtron 6. So this is something that as impedance requirements are getting tighter and tighter, the one way to do that is to tighten up some of the tolerance. The IPC spec, of course, doesn't go through the tighter tolerances with that, but here we're looking at a subset of the laminates that are identified as something we can offer as tightened up. So the thickness tolerance is plus or minus 5%, and also with the prepregs as well. So a tighter tolerance on that resin content. Panasonic does a real good job with controlling both the thickness tolerance for laminate and also the resin contents with it on prepregs. But here is as a controlled, identified way that they've come up with to help get to those tighter impedance projects with that. So this is something that's under development. I haven't seen anything yet that's available with that, so wanted to bring that up because it was one of the points that Bob was looking at with that. So this may be a solution to getting to those impedance projects that you were looking at. So that's something that we're looking forward to. And then finally, real quick, R5515, the RF applications. is something that it's in development. It's got a limited product offering right now, but really it's an antenna type RF application with that, automotive, millimeter wave radar, base station, those types of things. So we see that it's approaching the PTFE type properties with the low DK properties, and especially the low DF properties compared to MEG6 with it. But it's also a halogen-free product as a bonus with it. So that's one that's up and coming. Like I say, we've got limited cores that are available, limited product offering. It's still under development, working on some bond ply to go with that. But in those applications where that may be needed, some of the collision avoidance stuff or some other projects that may be out there, this may be a product that processes a little bit better than a PTFE, maybe more cost effective with that, and still get the performance out of it. So with that, I thank you all for putting up with that. I know it was a lot of slides, but I was hoping the pictures would say more than I would actually have to talk. So that's all I have for right now. We can open up for questions.
And yes, we're still all here. So yeah, this is Jim. So first off, before we get any questions, might be want to say thank you for the detail. I think you hit all the topics that are important to us, and we certainly appreciate the time you took to not only put this together but to present it to us. So again, thank you for taking the time to do that.
That's our pleasure. Thank you.
Any questions from anybody? Rick, how much of this is going to be available to us? I know that's the question you were waiting for, but
I think most of it, if not all of it. I'll run it by everyone to make sure we don't have anything in there that we can't release with that. But yeah, we should be able to make it available to you.
That's great. And of course, if it has Panasonic proprietary on it, then of course we know it falls under our NDA. So we understand that. Okay. Anybody? Bob?
I think we lost Bob partway through.
That's why it went so smooth.
I'm telling. All right. Well, with that, if there's no questions,
I have one question real quick. Is the MEG 4S going to replace the MEG 4 eventually?
Well, I think
I'll
that's
be willing to answer,
market demand.
I'll be willing to answer that one. MEG 4S has actually been commercial in Asia for 5 years. And because of the type of development that was being done there, especially with HDI, there was a lot more interest in MEG 4S there than there was here. Matrix has started to sell MEG 4S, but a lot of the designs that are out there call out Megtron 4, and a lot of the OEMs that we qualified Megtron 4 won't let us to change, won't let you guys change without a requalification, and so it's been very slow change here. So for the foreseeable future, Matrix and Panasonic will be making both.
Okay, thank you.
I have a question. Can you hear me?
Yes.
Okay, good. For some reason, I wasn't heard. It's Brian in San Jose. Question on Megtron halogen-free. How do you plan on referring to that? I mean, I keep hearing Megtron halogen-free, or R5375. That's kind of cumbersome. Are you going to call it Meg6H, Meg6RH, something more handy for communication with a customer and across this industry?
We call it halogen-free Meg6 right now, or Meg6HF. The actual number that will show up in the UL file will be the official kind of designation. I think that we are, as a Japanese company, pretty bad at pet names, and so Megtron and using Megtron in a series is a very good thing for us because it's very easy for people to understand it. Megtron 6 is a pretty easy thing for people to remember. I think for everybody's sake, Megtron 6 HF is or for the long form, halogen-free Meg 6 is going to be how it's referred to.
Okay. Anything else?
It seems like Brian's talking, but I'm not hearing him.
Oh no, he's not. I'm not talking, or I'm weirdly muted again. I don't know, but I wasn't talking though.
Okay. It's just the little the symbol on the screen.
Okay. Well, if that's it, again, I'll offer my thanks to the Panasonic team. This has been very, very helpful. So thank you. We'll look forward to getting whatever version you're able to send to us. I understand you may need to sanitize some things, and we get that. But we'll look forward to that. And, again, thank you very, very much. Hope everybody has a good day.
Great. Thank you all.
Yes, thank you. It's very good.
Great job, Rick. Thank you.
You have been removed from the call. Goodbye.